Have you ever shared an umbrella with someone during a rainstorm? That simple act of sharing can help us understand a powerful concept in chemistry: covalent bonding. Welcome back, young chemists. Today we are exploring how atoms like hydrogen and chlorine bond by sharing electrons to form stable molecules. A covalent bond is formed when two atoms share one or more pairs of electrons to achieve stability, just like the noble gases. Hydrogen aims for a duplet, which means two electrons in its outer shell. Chlorine, on the other hand, wants an octet, 8 electrons in its valence shell. Depending on how many electron pairs are shared, the bond may be single, double, or triple. Now, if the sharing is equal, as happens between two hydrogen atoms or two chlorine atoms, the result is a nonpolar covalent bond. But if the sharing is unequal, as in a water molecule, then the bond becomes polar covalent. Let's begin with the simplest molecule in the universe, the hydrogen molecule. Let's take a close look at hydrogen. A hydrogen atom has one electron. To become stable like helium, it needs one more electron, making a total of 2. When two hydrogen atoms come close, each contributes one electron. These two electrons are then shared between them, forming what we call a single covalent bond. This can be represented as hydrogen atom with one dot plus another hydrogen atom with one dot gives hydrogen colon hydrogen, or simply hydrogen dash hydrogen. This results in the formation of a hydrogen molecule, which we write in words as hydrogen to gas. Both atoms now feel like they have two electrons, completing the duplet structure just like helium. And that's why the hydrogen molecule is so stable. This principle isn't just theoretical. Hydrogen gas is used in fuel cells as a clean burning fuel and in the synthesis of ammonia in the Haber process. Let's now visualize the hydrogen molecule using orbit structure. Imagine two hydrogen atoms, each with a nucleus and a single electron revolving around it. As they approach, their electron orbits overlap, allowing the electrons to be shared in the same space. This overlapping region becomes the electron cloud where the shared pair resides. Both nuclei attract this shared pair, resulting in a strong bond between them, and this is what holds the hydrogen molecule together. In diagram form, you'll see two overlapping circles, each labeled hydrogen atom, and in between, two shared dots representing the shared pair of electrons. And that's how nature builds a stable molecule out of two simple atoms. Now, let's talk about chlorine, a heavier, more complex atom. A chlorine atom has 17 electrons with an electronic configuration of 2, 8, 7. That means it has 7 valence electrons and needs just one more to complete an octet, a stable outer shell with 8 electrons. So what happens when two chlorine atoms come near each other? Each shares one of its unpaired electrons, forming a single covalent bond. We represent this using the electron-dot structure. Chlorine atom with 7 dots plus another chlorine atom with 7 dots gives chlorine colon chlorine or chlorine dash chlorine. This forms the chlorine molecule, which we write as chlorine to gas. And yes, this is the same chlorine used in swimming pools and disinfectants, a real-world example of covalent bonding in action. Now, let's look at the orbit structure for the chlorine molecule. Each chlorine atom has 7 electrons in its outermost shell. When they come together, one unpaired electron from each atom is shared. This forms a single covalent bond. Each atom still retains 6 electrons as 3 lone pairs. So in the orbit structure, you'll see each chlorine atom with 3 lone pairs and one bonding pair that sits between them. This bonding pair is what makes the covalent bond, allowing both atoms to feel like they have 8 electrons, just like the noble gas argon. So the chlorine molecule, chlorine to gas, is held together by this mutual sharing, resulting in octet stability. Now that we've understood how covalent bonds form, let's explore the properties of covalent compounds. First, their physical states. Covalent compounds are usually gases, liquids, or soft solids. That's because the forces between their molecules are weak. They also have relatively low melting and boiling points. This is due to the weak intermolecular attractions, which don't require much energy to break. Next, covalent compounds generally do not conduct electricity. Unlike ionic compounds, they have no free ions or charged particles to carry current. When it comes to solubility, covalent compounds often dissolve in nonpolar solvents like benzene but are usually insoluble in water, a polar solvent. From carbon dioxide in soft drinks to methane in cooking gas, covalent compounds surround us, demonstrating the beauty and utility of electron sharing. So let's quickly revise what we learned today. Hydrogen atoms share one electron each to form hydrogen to gas, a molecule with a single covalent bond and a stable duplet configuration. Chlorine atoms do the same, sharing one electron each to form chlorine to gas, with both atoms attaining the stable octet configuration. These are classic examples of nonpolar covalent bonding, equal sharing between identical atoms. We used electron-dot structures and orbit diagrams to visualize this bonding, helping us understand how atoms achieve stability. Covalent compounds may be soft and low melting, but their importance is hard to overstate. They fuel our stoves, clean our water, and sustain our lives. I hope you now see how simple electron sharing leads to some of the most fundamental molecules in nature. Stay curious and keep connecting the dots of chemistry in your everyday world. In the next video, we'll discuss the structure of covalent compounds formed by oxygen and nitrogen, where multiple bonds and new patterns of sharing await us. See you there.